So with counting and statistics, there's lots of new words, and the first one we come to is permutation. Permutation simply describes an arrangement of a group of symbols, objects or people in a definite order. So we've got an example of that with the permutations of the letter A, B, and C. And if we think about that, well, how many, if we did our little box thing again, we could go, well, how many times could we, different things could we put in box 1? 3. But if we're using one of the letters up, we won't use it in the next box because we want to use all 3 letters. So there's only 2 in our next box, and then there'll only be 1 left over. Now, if we think of that and actually wrote it out, that would be ABC, ACB, BAC, BCA, CAB, and CBA. And there what we're doing is we're actually assuming that all the letters are to be used. Alright, so that's actually equal to 6 possible arrangements. What about though if we were using 2 letters at a time? So not 3 anymore, we were only using 2 letters at a time. Well, think about that. We can still have 3 in the first box, and we'll only have to be able to have 2 in the second box. So again, that's 6 possible arrangements, and they would be AB, BA, AC, CA, BC, and CB. What about then if we only use 1 letter at a time? Okay, so using 1 letter at a time. Well, obviously we're only allowed to use 1 letter, so it's either going to be A, B, or C. So there are 3 arrangements. Alright, so we're just arranging these in a specific order. Now, if we're calculating this for a bigger scenario where we can't just list them all out, it might be a little bit harder, we'll do what we did up here, and we'll use the addition and sometimes or, so sometimes we'll use one or the other, or we might use both, the addition or multiplication rules. Right? So let's go. Let's try a specific example. So a 3-digit number is made up using the digits or the numbers 0, 2, 3, 5, and 6. Alright? So it's made up using, and 9. Now you can only use them once each at most. Now you don't actually, you could use them more, you don't have to use all of them, but you can only use them at most once each. So how many different numbers are formed if there are no restrictions? Alright? So, well, think about it. Box, box, box. So no restrictions. Well, this first number up here though can't be 0, can it? Because if that was 0, that would mean that you wouldn't get a 3-digit number, because that 0 effectively doesn't count. So there's only 5 options, because you've got a total of 6 up here, but you can't use 0, so there are 5 options there. Then we're doing our second choice. I'm just going to write can't be 0, just so you understand why that's 5. For our second choice, we've got 0 as a possibility, but one of the others has been taken away, so we've got 5 again. And then for our third choice, 2 numbers have been taken away, so we've got 4. So the number of 3-digit real numbers is just going to be 5 times 5 times 4, which is 100. Now for the next one, the number must be greater than 500. So obviously the first letter, or first number, is only able to be 5, 6, or 9 to give me a number that's greater than 500. So I've only got 3 options. Then I've picked one of those numbers. For the next number, I can choose any of them. So I'm going to have 5 numbers to pick from because I've already picked one. And then for the last number, I'm going to have 4 because I've already picked 2. So that means that the number of 3-digit real numbers greater than 500 is going to be 3 times 5 times 4, which is 60. And the final one is a little bit trickier. What's going to go if the number is even? Alright, so if the number is even, think about it, it means it must end in 2 or 6 or 0. But because that 0 is a little bit of a different option, we're going to split this up. We're going to split it up into end in 0. So 2 and 6 are pretty much the same scenario, whereas 0 is a different scenario. So we're going to split this up into either ends in 0 or ends with 2 or 6. Alright, so let's think about, remember, or means add. Let's do our box things. So we're going to do a separate one for these two scenarios. So if it ends in 0, well, you can't use 0 for the first number, so that's 5. You can't use 0 for the second number, we've already used another number, so that's 4 left. The only thing you can use for the third number is 0, so you've only got one chance. Now if it ends with 2 or 6, we can't use 0 for the first number. We also can't use both 2 and 6, right? We could use one of them, but we can't use both of them, so that leaves us with 4 there. Then with our second choice, it can be 0, but one number is already gone. That's our first, with our first choice, we already took one away, and we still need to make sure that we've got an even number, so we still can't pick one of the evens. So that leaves us with 4 to choose from. And then secondly, thirdly, the last number is either 2 or 6, so we've got 2 choices. So if we're trying to answer this fully, we'd say the number of even numbers is going to equal 20, 5 times 4 times 1, plus 4 times 4 times 2. And that's going to be 20 plus 32, which is 52. Alright. Now with permutation questions, products are very common. So they can be represented really efficiently using something called factorial notation. So n factorial, or the factorial of n, is represented by the symbol n prime, we call it. Looks like n exclamation mark, but we call it n prime. So that's n factorial, or the factorial of n. And so that is just that n primed is equal to n times n take 1 times n take 2 times all the way down to 3 times 2 times 1. So for example, I'm just going to put a quick example here. If I had 4 prime or 4 factorial, that would be 4 times 3 times 2 times 1. Now this is helpful if you're doing something in where it's going, your product is going down by 1 every time. It's also helpful if we've got n objects that are being arranged in groups of size r. And we would represent that by P, standing for permutation, of n objects in groups of size r. And that has a specific formula. That formula is that is equal to n factorial, so the n objects, divided by n take r factorial, where r is the size of your group. So that is actually going to give you n times n take 1 times n take 2 times all the way up to n take r plus 1. Alright, that's what that will actually give you, because if you think about it, n primed is actually n times, you don't have to write this down, but it's n times n take 1 times n take 2 all the way down to 3 times 2 times 1, and n take r prime. So say n, say if r equaled 2, say that would be n take 2 times n take 1 times all the way down to 3 times 2 times 1. And so if we cancelled stuff, we could cancel that with all of that, and we'd be left with n times n take 1, which is and take 1, well, 2 is r, so that would make sense in this case, because it would be negative 2 plus 1, which is negative 1. So you get n take 1 corresponding to your final term. If you don't really get the algebra of that, don't worry too much. This is the formula that you will be able to use if you're arranging n objects in groups of size r. Okay, so I'm just going to clear up some of that mess. Before we go and do some examples, just know that 0 primed is actually equal to 1. And again, you wouldn't ever have to write this out, but it's worth noting why that is. If you look down here, n primed is actually equal to n times n take 1 primed. Now that makes sense, hopefully, because you remember that n, it's doing something weird, n primed is equal to n times n take 1 times n take 2, all the way down to 3 times 2 times 1. Now if you wrote that part in a different way, that is actually the same as n take 1 primed. So you can therefore write n primed as n times n take 1 primed. That's why you can write that. Now n take 1 primed is the same as this. Okay, makes sense because you can just cancel those n's. We've just put multiplied by n and divided by n, so it's actually equal to the same thing as that. So that is equal to n primed divided by n, because we just said that this bit up the top is equal to n primed. So we've got n take 1 primed is n primed over n. So then if we go n equals 1, we would get 1 take 1 primed. So that's 0 primed. If we put n equals 1 and then put that into the formula, we get 1 take 1 primed equals 1 primed over 1. Now 1 primed is just 1 times, well, anything that gets to 1, so we're already at 1, so we don't times by anything. Divided by 1, it's going to be 1 divided by 1, which is equal to 1. So that is why 0 primed is not actually equal to 0, it's equal to 1. Now you might go, well, does that mean therefore that 0 primed is equal to 1 prime? The answer to that is yes. So that's that bit. So let's do some examples and see how this relates to what we were talking about before. So if we're just evaluating these following factorials, we call them. So remember, if it's got that exclamation mark, we generally call it a factorial. 6 primed is just going to equal 6 times 5 times 4 times 3 times 2 and times 1. And so that's going to equal 720. Now if we look at 10 primed over 8 primed, well, I'm just going to show you a quick way of doing this. Instead of writing this all out, we're just going to write that as 10 times 9 times 8 primed divided by 8 primed. Alright, and then we'll cancel the 8 primes and we'll get 10 times 9, which is just equal to 90. Then if we want to write the following using factorial notation, this one's a little bit trickier, but hopefully you can see that if we want to get n plus 2 times n plus 1, alright, n plus 2 primed would be n times 2 times n times 1 times n take 1 times n take 2, etc. So if we divide this by n primed, we're just going to be left with n plus 2 times n plus 1. Now if you want to assure yourself of that, just write out what n plus 2 is and then write out what n primed is, and you'll see that it is correct and I am not lying to you. And then similarly for L 11 on its own, well, 11 on its own, if we want to write that as factorial, that's just the same as 11 primed over 10 primed, because 11 primed is 11 times 10 times 9 times 8 times 7, 8 times 7 times 6, blah 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 blah, over 10 primed, which is 10 times 9 times 8 times 7 times 6 times blah 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 blah. So cancel, and we just get left with 11. Alright, number 4. Find, and our last example before you can just do some on your own, find using factorial notations the number of permutations, remember that's the definition of a permutation that we talked about before, there are of the letters A, B, C, D, E, and F, using all of the letters. Well, the number of arrangements is actually just 6 prime. Because you think, for the first time you pick something, you'd have 6 choices. For the second time, you'd have 5. Third time, you'd have 4. Fourth time, you'd have 3, etc., etc. You do 6 times 5 times 4 times 3 times 2 times 1. So we're doing it in factorial notation, so we'd leave it as 6 prime. If, or however, we weren't doing it in factorial notation and just in normal notation, you would just leave it as 6 times 5 times 4 times 3 times 2 times 1, simplified. Now if we're doing 2 letters at the time, that's where we use that formula that we talked about before, where NPR, so N is the number of objects, 6, P is the permutation, and R is the size of the group, so 6P and 2 is going to be equal to N primed divided by N take R. Take R, not take 2, if I'm writing in general form, and take R primed. So in this case, it's going to equal N prime, so 6 prime, divided by N, 6, take size of the group, or R, 2. So it would be 6 primed over 4 primed. And that would be your answer to that. So that's all it is. They're just a way of helping you write things in a bit more of a clearer or simpler fashion. Thanks. Bye.